All right, we have a Codeforces Div 2 today. I only have a limited amount of time, probably like 45 minutes, so let's see how much we can do. Until it's sorted. Oh, that's weird. That's very weird. 0, okay. If some number is bigger than the next number, then it's just the max. Otherwise it's... Oh, it's the max of... Oh... The max of the ones where some number is bigger than the next number, right? I think that's what it is. Yeah, because... Yeah, that makes sense. Okay, so... So many typos. Right. No, not minus one, plus one. How do I do that? Right. That was very slow. All right, let's see. If A is not equal to BI, and the sum. Oh, interesting. Does it exist? Positive. That would be positive. I think just the sum has to be big enough. At least half of them have. Or the sum has to be at least. No, yes. Oh, and n has to be not 1. n greater 1 and sum greater than equal to n plus n plus 1 by 2 plus no. No, that's not quite right, is it? Because 1, 1, 1, 1, 1, 1, 1, 5, 4. This is not a yes. This just needs to be, because it needs to be 2, 2, 2, 2, 2, 2, 1, right? I would need this alternative. Two, otherwise 1. And we need some, we need all. This needs to be a no. Okay, I think that's what I mean. Great. All right, come see. Maybe you just start from somewhere and then you just go left. 6, 7. Yeah. Yeah, that's basically. Isn't that it? AJ minus, or start AI plus I minus J. That's how much minus AJ. If need is going to have a break. Otherwise, have minus plus need. Right, plus I minus J. Is that it? Or like it's this wrong? Where's... Yeah, okay, this one is weird. Now, apparently you can do something here. 6, 6, 5. Set this to 5. Set this to 5. 6, 7. How is this 7? How do you make a 7? 5. That takes 4. 5. That takes 1. So I set this to 6, so it takes 5 steps. Set this to 5? What? Set this to 5. 4. How do you make 7? What? We get to 4 and then you go 5, 6, 7. Ooh, that's interesting. How far behind am I? Once you have a tree and then you have... You should just pick it so that it splits it as evenly as possible. Oh, but no, that's not quite, that's not quite. So, okay. Why can't I solve this? Like, yeah, when is that useful? Can we achieve x value? So we want this one to be x. So this is x minus 1, which means maybe I can do something like that. All right. Goal minus genocide. fast enough and squared log, that's fine. I should use, no, whatever. It's fine. I think E1 is the play, given how fast we lit it. I'm not even top 20. Wow. 4 minutes. Wow. Okay. Okay, let's see, let's see. Okay, well you have the root, right? You have the root. You listen. You have the root. You're like knapsacking the subtrees of the root. Yeah, I mean, three and one, right? Like 3 times 1. Yeah, let's see if red and blue here. Either all red or all blue will be better. Yeah, that's right, that's right. Okay, yeah, so what are we doing here? We are what is this? Okay, that's what we're doing, right? And then just use bit sets. It's really like array. It's just int, whatever. How long does this take? I mean, this is once per. This is quite right. Is it play D or E2? D is worth more points, so I think probably the place D. Like 20 minutes left, okay. Really? That was not the right order. Resolve. Okay, never mind. I have to kill dead set spin, she's 1 million. Actually, is that too big? I mean, it's gotta be too big, right? They must have tested it. D is salt. E2 is salt. Basically, adding it to the end would not affect. Adding to the beginning would. Yeah, really, wherever it is, if you go from here to here, it adds that many. If you go from here to here, it's 0. Right, okay, so that's. Yeah, like we compare everything, right? So then it's like. We only have certain remaining positions that are candidates. We have this positions that are candidates in the pair. I feel like that works. If after yeah, I mean, shouldn't add anything, right? Here, not which. So candidates. Is it from the plus? It's kind of weird, but yeah. One, two has 0 inversions, 2, 3 has 1, 2, 4 has 4. Wow, okay. in the queue. We can pass some pretests. E2, we have to. I have something for this, but what is it? It's like square root bit set. What is it? Oh, it's like if you have a largest. Yeah, otherwise you do this thing. Is that what it is? I think it's in the CSES folder. How many of these were? It's like school excursion. There's the problem. Possible subsets. Okay, what is this? Yeah. So like this thing. Computer. So n square root of n over 64. Like I think this is the plane. So. All right, now I think we're going to do this. Otherwise, we do the knapsack. But the knapsack, we do the square root version. Okay, so we I think we can just do this. N max by 2, we have n, what is n? So it's getting a little weird. Okay, so What? Oh, that's so dumb. So what is this? And then, oh, then you also add the AVX, obviously. And then you use 6 plus 20. I think that's the play. E2, because this, yeah, we're only gonna, yeah, I think we're good. How? I thought this would be fine. I need to check out my solutions. Which one is the fastest? This one? C++ 17. But 2064 is pretty close. Just steps this. This thing. Alright, so I thought this was the play. Those are all small and you can do the thing. Screw that. Oh. Do I have some bug here? Oh. Oh, we need a custom size bit set. Something like this. Okay, I'll just do this. That's the problem, right? Because we have Right, but at every level we're still doing, yeah, that's the problem. Okay. Cool. So we're gonna do this custom bit set. How do I use this? I don't know how to use this. Custom bit set. Or ship. Okay, okay, great. And you init it with the sum. Okay, custom bit set. Let's kill this. Custom bit set. Custom bit set. How many bits do you need? N plus 1. What is it? Set. I don't need this. Probably one more. Yeah. I think this is it. That penalty might cost me. Might cost me. Alright, just in time I need to leave. Perfect. Did I need... I guess it's good. Got it? Great. Okay. All right, I'm back from lunch. Ended up being pretty clutch here. I only had 45 minutes to do the contest before I had to run for lunch, and managed to finish the last problem in just under 43 minutes. And yeah, even though I had that one penalty, ended up holding onto first place. So pretty happy with this. I think my first win in a little while, but let's dive into these problems. Let's talk about them. Cool. So first we have problem A. Basically, you have one operation you can do. You decrement each AI, but you don't go below 0. And you want to do it until it's sorted. And so there's a couple of key insights here. First of all, you can always get it sorted because you can get everything to 0. So that's guaranteed you can do it. And you want to know if you can do it in fewer. The way to think about this basically is when you have two numbers, if they're already in order, this operation will never bring them out of order, right? If they're already in sort of order, you'll do that, and then you'll stay at 0, 0. So at no point does it become unsorted. But if you have them out of order, you need to go until it's 0, 0, and then you'll get them sorted. So that's basically the key insight here. When you have two consecutive numbers out of order, you have to do at least the bigger number, at least that many operations. And so actually that's just the solution to the problem. We just check two consecutive numbers. If they're out of order, then we need to maximize our number of operations with AI. And if you think about doing that number of operations, you will basically fix every out of order pair. And so every consecutive pair will be in order and you'll be good. Yeah, so that's A. Takes some thinking, but the code is pretty simple. Problem B. Right, so problem B, you need to find another array B with the same sum as A, but none of the values match. So the idea here is basically, in general, you can do it unless the sum is kind of too small in a sense. So for example, like 1, 2, 1, 1, 1, the sum is just kind of too small. One of these ones is going to match up in B. Otherwise, you won't get a big enough, or otherwise your sum will be too big. And basically the idea is just to compute the alternative sum, meaning what is the lowest possible sum we could get if none of the numbers match. So in this case, we would have to go 2, 1, 2, 2, 2. For a case like this, we would go 1, 2, 1, 1. We're just going to compute that, and we need our sum to be at least that much, right? That is the min possible sum for an array where everything is different. And also n has to be greater than 1. If n is 1, there's no way to do it, right? And then I claim if n is greater than 1 and the sum is big enough, then you can do it. Yeah, so basically the idea is you just take that alternative array and first of all, if everything in my array, my original array is bigger than 1, then I can do 1, 1, 1, 1, 1, and then put all the rest of it in the last number, and that will make them all different, right? Otherwise, I have at least a 1, 1 in my array, for example, this. So my alternative array is 1, 2, 1, 1, and then I can pile all the value into that first 2. And in that case, it'll be different. So a couple cases to think about, but basically they all work out. And so these are the only constraints you really need. And so that's it. So again, kind of a thinking problem, but once you think through it, the code is pretty short again. Yeah, one little thing to be careful of is just C++ tip. If you use accumulate, if you just put in a 0 here, you will overflow, because the type of the output will be the same as the type of this initial value. That's why I give it, this is essentially a cast to int64. This is like a int64 constant. And so that's how I do it. Other thing you can do is you can do 0LL. That's very common as well. So a couple options, just make sure this is a 64-bit value, and you'll be good to go. And this is true even though A is int64. So you gotta be careful there. All right, problem C. Right, so in your operation problem C, you can increment AI by 1 if AI is less than or equal to AI plus 1. And then you want to maximize the max possible value of the max value in the array. This is a lot of maximizing. But you can only do the operation was k times. So I tried a couple things here. I actually did a wrong approach here in n squared. And the tricky sample, I failed this sample. And this sample is tricky because my approach was just to start from a number and just go left and kind of greedily go as far as you can. But to do this case, you actually take this. You have 6 operations. You take 6, 5, 4, 1, 5. You take 3 operations to bump this to 4, 1 operation to do 5, 1 operation to do 6, 1 more operation to do 7. And so in 6 operations, we can actually get a value of 7, which does not happen in this approach. This approach only gets 6. So the key idea I ended up having here was we can binary search on the answer. So we have a target number. So we have a goal. We want to get to this goal. So this is standard binary search. We want to check if we can get this goal. Here's our goal. And then for every index, I search for, or I'm trying to check, can I make AI equal to goal? In order to make AI equal to goal, either AI is already equal to goal, or I increment it up to goal. If I'm incrementing it up to goal, then I need AI plus 1, namely this. The next element needs to reach goal minus 1. And so I can continue onward. If I can make that value equal goal minus 1, then we can do it. Otherwise, I need to make the value after it equal goal minus 2, and so on. And so at some point, we need to run into a value that's at least big enough compared to what we need. And then in that case, we can return true. Otherwise, we know how many steps we need here. If we don't have enough steps left, then we failed. Otherwise, we keep going. But if we reach the end without ever seeing a number that's big enough, we can't make it because we cannot increment the last number. Remember. And so this is just a quick n squared approach to figure out if you can make the number. Gives you a check. You can run your binary search, and now you have n squared times log a complexity, which is fine here. This problem was a little tricky. Yeah, like I said, I had that wrong approach. Had to kind of go back and figure out how to solve it properly. But this ends up being, once you think of the binary search, this check ends up being more straightforward. All right, let's talk about problem D. Yeah, okay. Yeah, so you get the number of inversions in the array, and then each query costs this much. And you want to spend at most 5 n squared coins. Okay, so the first thing I thought about was, how can I solve this problem not worrying about the coins? If I just do as many queries as I want, how do I solve the problem? I need to find the max value in the array. Well, basically, if you have the location of the max value, right? If this is your max value, then when you query, basically this value is bigger than everything else, right? So if this subarray has X inversions, then this subarray right here, after adding the max value to the right, also has X inversions, right? And then similarly, and what that tells us, in fact, is that this number is bigger than all of these numbers. Similarly, this array, or rather, if this array has Y inversions, then this subarray should have Y plus 4 inversions, because this should make an inversion with every value here, which also tells us that it's bigger than everything afterward. And so that's the idea. If we were to query that for every index, then we would find who the maximum is, because only the maximum can verify that. But obviously that's too expensive. So what I ended up thinking about instead is, well, if we have consecutive pairs, we can compare them, right? If we have A and B consecutive in the array, we just query the subarray. If it's 1, we know A is bigger than B. If it's 0, we know A is less than B, based on inversions, right? And so then we end up with a bunch of peaks. So if we know A is less than B, right, we can immediately throw away A, and vice versa. If A is greater than B, we can throw away B. So we end up with a bunch of candidates, like separated by spaces, that could still be the max. And then I realized what you can do is if you have A, B, where A and B are candidates, but you've already thrown these out. In other words, you know that A is bigger than all of these values, and B is bigger than all of these values. You can compare A and B, right? Because first you query A and everything. Let's say that's X. And then you query A and everything with B. And if B is the biggest, B is bigger than A, it will still be X. B is biggest. But if it's X plus 1, that means A is the biggest. And so that gives you a way to tell which of A and B are bigger, and you can eliminate one of them, right? You can ultimately end up with either get rid of A or you get rid of B. So that's kind of the idea here. So you start with something like this, and then you want to take any consecutive pair, compare them, and then throw one of them away, and then kind of repeat, right? And maybe you compare these two, you throw this away, and then you compare these two, and then you realize that this one is the biggest one, right? The only thing we have to worry about is the cost. So the idea that I had here is you just do a simple greedy, which is you take the closest two together and you compare them. So in this case, you take these two, right? It's kind of intuitive. You minimize the cost of your current query because this distance is the smallest, and then you'll get rid of one of them. And then again, you take the closest two, which would be these two, and you get rid of one of them. And then you take the closest two. These are the last two, so you query them. And so that's the solution that I did. Basically, take those candidates. Your candidate starts as everything, and find them in gap, query those two, erase one of them, and repeat until there's one left. That's it. So the question is, how many queries do we do, or what is the cost? Basically, one easy bound you can show is that your last query is at most size n, right? So that costs n squared. It's actually n minus 1 squared, but anyway, n squared. Your second to last query, which means there are going to be 3 things, right? It's going to be at most n over 2, right? The reason being that you're picking the smaller of this versus this. Your third to last query is at most n over 3 squared, and so on. That's kind of that's like a quick bound. Obviously, this whole thing has a times 2 because we do 2 queries per pair, right? We do this, and then we do this. But this actually ends up being 1 plus 1 over 4 plus 1 over 9 plus 16. And then you can look this up. This is just kind of a known math thing, but the sum of the inverse squares is, it's roughly 1.64. It turns out it's actually pi squared over 6, which is kind of crazy. But anyway, the point is it's bounded. 1.64 is a constant. So basically we end up being 1.64 times 2 times n squared, which is, you know, something like 3.28. I guess it would round to 3.29. But anyway, it's under 5 and it's good. It turns out there's another nice approach on this problem that it's a little worse for queries, but it ends up being really nice for the code. It's just a really simple div conquer. So basically you take the left half of the array, solve for the biggest one, take the right half of the array, solve for the biggest one, and then you just do the thing I mentioned to query between them. And so you can show that basically this is f of n equals n squared, because the worst case is your last query is everything, I guess 2n squared, plus 2 f of n over 2. And then this is the whole master theorem. This is O of n squared. If you actually map it out, it's it's going to be 2n squared plus 2 n over 2 squared, right? Let's get rid of this 2, actually. Let's get rid of this 2. We'll deal with the 2 later. There's 2 of these, right? There's 4 of these because it expands out. And this ends up being n squared plus n squared over 2 plus n squared over 4. This ends up being 2n squared, and then we have to multiply the whole thing by 2, so we get 4n squared. So this is a little worse, but still under 5, and so it also works, and the code is very short. Quick shout out to AG for that code. And then that's problem D. And then finally, let's talk problem E. Yeah, so E1, you have the same problem but as E2, but n is only up to 5,000. So basically, you want to maximize the number of, you want to label the vertices 1 through n with a permutation, and you want to find the number of pairs of vertices uv where AU is less than A, LCA UV is less than AV. And you want to maximize the number of pairs. So if we think about a tree, we can think about like, there's a root, right? And then there's some subtrees, This is a very abstract drawing of a tree. So here's a root, here's one subtree, here's another subtree. So this is like a root with subtrees of size 3 to 5, right? And basically what we're doing is some of the values in each subtree will be bigger than the value of the root, and some of them will be smaller. And we want to do basically sum of, like sum of, UV where some, well, just a count of UV where U is in UV are in diff subtrees, and AU less than a root, and AV greater than a root. So another way to think about this is we're going to paint all these nodes either red or blue, and then we want to count how many red-blue pairs are not in the same subtree. Right? Okay, so first claim I'm going to make: every subtree should be fully red or fully blue. How do we think about that? Well, let's fix one subtree. Let's take this subtree with 3 things, right? Let's say it has some red and some blue. Well, how does our function change if we take a red node and change it to blue? Basically, we lose the number of pairs, which is the number of blue nodes in the other subtrees. We gain the number of pairs, which is the number of red nodes in the other subtrees, right? And then vice versa. If we swap blue to red, it's the opposite. It's a negative effect of that. So one of those effects is non-negative. It's not necessarily positive, but it's at least 0, right? So we can, if we have an optimal solution, we can adjust each subtree to be monochromatic, a single color, without making the function worse. And we can do that for every subtree. And so there is an optimal solution where every subtree is a single color. So now that we know that, actually what we're looking for is we're just taking every subtree size and we want to, like 2, 3, 5, we want to divide them up to make basically as close to half of the total sum as possible. So in this case, we do 2, 3 red and we do 5 blue, which gives us 5 times 5 pairs, which is the best we can do. So this is just a knapsack problem now. So basically, we're going to, we're just going to run knapsack to solve this. Here we just find stuff about the tree, and then we have the key thing here, which is a knapsack. For every subtree, we just run our knapsack on a bit set. We have the sum. We're just looking for as close to sum over 2 as possible. And then we take this product. And that's it. That's E1. Very simple. Runs in quadratic time. And so we're good. And so E2 is the same problem, but n is up to 1 million. All right, so what are we going to do now? So this is a n squared over 64 because of the bit sets. But for 1 million, n squared is huge. It's a trillion, so that's not going to be any good. So what can we do? So it turns out there's this approach. There's this approach for the subset knapsack that improves upon the complexity. So basically the idea is the worst case. So the thing is, all of these add up to n, right? And then we're doing a knapsack on n. But the worst case for this knapsack is you have n things of size 1, right? But n things of size 1 is pretty silly as a knapsack. Like, obviously you can make everything. So how do we make that better? Well, the core idea here is we can basically, the idea is if your subtrees, if you have, or if your knapsack objects, if you have just 1 1, then you have to do that. If you have 2 1s, then that actually still ends up working out the same. But if you have a lot of 1s, right? Let's say you have a ton of 1s. Well, we could replace these 2 1s with a 2, and we wouldn't lose anything, right? And then similarly here, replace them with a 2, we wouldn't lose anything. As long as you keep at least 1 more 1 remaining, right? So if you have at least 3 1s, you can take pairs of them and replace them with the 2. And your subsets are still the same. Right, so when you have 5 1s, you can replace them with 1 2 2. And then let's say you have another 2, you can replace this 2 2 with 4, and so on. So that's the idea. So basically, here we're just counting frequencies of sizes. If the frequency is at least 3, you can just push up a bunch of them to twice the number, right? And now what we've done is every number's frequency is bounded by 2. So on any individual number, we can only do 2 iterations of this knapsack at most. And now we have a square root n bound because if you have to have distinct numbers that add up to n, you can have only at most square root n. So now this becomes n square root n over 64. So this is the key idea that we use here. And the funny thing is that since bit set constant factor is so good, 1 million, 10 to the 6 times 10 to the 3rd, which is 10 to the 9th, is still totally fine. The thing that's a little tricky here, we need to do a little bit more to improve this. So first of all, we use kind of a divide and conquer heavy light idea, which is that if, basically, if let's say we have a really tall tree, right, where one subtree is by far the biggest, we actually don't need to run knapsack, right? Because we're just trying to divide it as evenly as possible. If you have 1 1 1 10, right? You know you're going to split it into 3 and 10. So you can just do that. So that is what we do here. If the max subtree is at least half the sum, you just take it as one side and you take the rest as the other side. Otherwise, it will, satisfy a nice like kind of master theorem div conquer property. And then we run our knapsack. The knapsack looks just like this. It's right here. This is the idea. N squared n over 64. And then check the answer and then go down. And then we do this for everything. So it's kind of a recursive thing. It's not actually recursive, but it's like the div conquer idea. And so then we have the usual master theorem idea applied to, in this case, n to the 1.5 divided by 64 plus 2f n over 2. And if we apply master theorem here, the complexity is still just n to the 1.5, and then we still have to divide by 64. The reason being that this exponent is more than 1. And so that's our complexity for this problem, n to the 1.5 divided by 64, except actually there is a problem, which is that in the knapsack, you cannot just blindly make a bit set of the max size, right? Which is what I did here originally. This is how I got my TLE in the first place. The reason for that is that actually screws up this recurrence. It's not that anymore. It's like, it's big N times n to the 0.5, right? And so now we can just factor out this big N. It's just n times gn, where gn equals right, and now gn is actually going to be gn is just n, I think, in this case. And so now we have a problem because now we have n, big N times little n, which is just n squared. Now we're quadratic. So the way we have to deal with that is we have to actually make the bit set only as big as we need it to be. The way I did that is I have a custom bit set implementation that I just toss in here, and it just does the OR shift operation that we need. But there are some other ways you can do this. People did some funny, tricky things. For example, AG did this check for different powers of 10, where they use different bit set sizes. Nick did this, which is also very funny. 64, 128. Just checks every power of 2 and then makes a bit set of that size. And the editorial also has something. This is actually pretty cool. I didn't know you could do this. But you template with an int that defaults to 1. If n is greater than or equal to length, you recurse onto double your length with n. And you need to set this maximum so that the recursion will stop, because the compiler will actually evaluate this recursion. So the compiler kind of generates 20 different versions of this function, 1 for 1, 1 for 2, 1 for 4, and so on. And then all of those become options. You can also, it's kind of cool, you can make this less jumpy. If you don't want it 2x every time, you can make it, 1.5x or whatever you want. So it's a pretty cool trick. This actually is just like a general solution to the bit set not being the right size problem, because you have to decide the bit set size at compile time. You can just exponentially increase, and so you'll never be more than 2x what you need. So a bunch of different ideas here, but that's the key thing. Funny thing is, I encountered this technique from it was like a CSES problem. It's called school excursion, and so this was where I originally learned this technique. But yeah, I ended up having one of the fastest times on this problem. I haven't done any CSES in a while, but I just remembered this problem. I was looking at this one, and yeah. Anyway, fun little contest. Fun to clutch it out before lunch, I guess. That's definitely a new one for me. Haven't got a first place in a while, so nice to get it again. But anyway, thanks for checking this out, and I'll see you in the next one.